Okay, so our next section 2, which is about curves, polygons, and circles. A lot of it's kind of definition things. And there's also some things about triangles relative to the some of the angles in a triangle, things like that. So the first couple of problems are going to be just the general fill in the blank kind of things. So fill in the blank. Segment joining 2 points in a circle is called, well, it's called a chord. And so here's a circle. And if you have a line drawing between parts on the circle, that's a chord. And this is a chord. And this is a chord. So there are many different chords. There are an infinite number of chords. But they don't go to the center of the circle. They just go to from different points on the circle. Okay, question number 2. The segment joining the center of a circle to a point on the circle is called what? Well, there's probably 2 answers you might think of. And one might be radius, one might be diameter. Well, the radius is from the center of the circle. And this is the diameter. And if you want to find the center, you actually, if you took two of the diameters and found the middle like that, the cross, so if these are diameters, they're going to cross right in the center. And from the center to the circle is constant from this point, and that's called a radius. So the first answer was chord. A regular triangle is called an equilateral triangle. Okay, so equilateral means that all the sides are the same. They have the same length, and also all the angles are the same. And they turn out to be 60 degrees. Excuse me. So there's isosceles triangles, which are ones that have 2 sides equal and 2 angles equal. So it's also called a regular triangle. And again, equal angles, which are equal to 60 degrees, because the sum of the angles inside of a triangle have to equal 180. So if they're equal, then you take 180 is equal to 3x. X is equal to 60. And question 4 is, a chord that contains the center of the circle is called the, okay, well, it's actually over here. A chord that includes the center is the diameter. And the diameter is twice the radius. So the answer is diameter. And we know that the diameter is equal to 2 times the radius. Okay, next couple of questions ask you relative to shapes. Number 5 says, a rhombus is an example of a regular polygon. So what is a regular polygon defined as? So we'll go back and look in the book here, see if we can find out what regular polygon says. A polygon may or may not be convex. Polygons with all sides equal and all angles equal are regular polygons. So a rhombus, if we go over to the page 459 at the bottom, you see that a rhombus has the same length sides, but the angles are not the same. So a regular polygon has to have sides and equals. So a square would be an example of a regular polygon. You can see the green figures in the bottom of page 458. So an equilateral triangle, a square, a pentagon, a hexagon, whatever the next one is. That's I think the septagon, polygon. What's 6? Hexagon. A is an octagon. Okay, so the answer to number 5 is a rhombus is an example of a regular polygon. So that's false. It's not a regular polygon. Okay, number 6. If a triangle is isosceles, then it is not scalene. Okay, so what is a scalene triangle? So let's go look page 459. So we look at the types of triangles, and you see a scalene triangle is there at the lower right-hand corner, and it has those little marks, which mean that the sides are not equal to each other. None of the sides are equal to each other. Whereas you see that an isosceles triangle has two sides equal to each other, and an equilateral triangle has all three sides equal to each other. So when it says, if a triangle is isosceles, then it is not scalene. Okay, so because two sides are equal to each other, then you can't have all three sides not equal to each other. So it's true that an isosceles triangle cannot be a scalene triangle. Okay, number 7. A triangle can have more than one obtuse angle. Okay, an obtuse angle, again, if you look here, okay, actually I didn't see the previous section, but an obtuse angle is one that's greater than 90 degrees but less than 180. So if you had two angles that were greater than 90, you add this together and you get more than 180 degrees. So there's no way that you can have two angles greater than 90 degrees. So if one's greater than 90, the other two must be less than 90. And they all add up to 180. So number 7 is false. You cannot have more than two obtuse angles. You can't have more than one obtuse angle. A square is both a rectangle and a polygon, parallelogram. Okay, so if we go look, see what a square is, on page 459 it says a square is a rectangle, so that's definitely true. And then we look up for parallelogram. The parallelogram is a quadrilateral with two pairs of parallel sides. So a square has two parallel sides, so a square is a parallelogram. A parallelogram may not necessarily be a square. It's almost the kind of most specialized case of a square is the most specialized case of a parallelogram because it has parallel lines, but so does a rectangle, so does a rhombus. A square has equal sides, whereas a rectangle has unequal sides. Well, it doesn't have to have equal sides. A rectangle could be a square. A rectangle could be a square, but that's a very specific case of it. So it's true. Number 9 says a square must be a rhombus. So again, looking at page 459, a rhombus is a parallelogram with all sides having equal length. So yes, a square fits those requirements. It is a parallelogram, and it has sides with all equal length. The square has a special case that all angles are 90 degrees, whereas a rhombus, two of the angles are the same. Two of the 4 angles, 2 of them are the same. So number 9 is true. Okay, let's go up to 10 here. A rhombus must be a square. Well, that's false. A square is a special kind of rhombus. But the rhombus, if you look at again, look at figure on page bottom of page 459. The rhombus there is not a square. It's only a square when the angles are all 90 degrees. Okay, in your own words, explain the distinction between a square and a rhombus. Well, the distinction is the square has 4 90-degree angles, whereas the rhombus has 2 angles that are the same, and the other 2 angles are the same. So it's kind of skewed. It's like you take a square and you smush it down. And what common traffic sign in the United States is in the shape of an octagon? So let's go to page 458, down the bottom, regular polygons. So we look at it and we see that the bottom one on the right-hand side has 8 sides, and that is what the shape of the stop sign is. And that's, if we go to table 3, we see that 8 sides is an octagon. So number 12 is octagon. 11, I'll let you write out what you want to do there. Okay, now we're going to start going through every third problem like we normally do. So we'll start at 13 and go keep going. Just writing down the numbers so I can keep these straight. And if we change anything, we'll reflect it. But identify each curve as closed, simple, closed, both, or neither. Okay, so 13. So it's closed because there's no break in the circle. There's no break in the curve. So it's closed, and it's simple because it doesn't cross over each other. So that's the, so in this case it's both. It's simple because it doesn't intersect itself, and it's closed because there's no end to it. So that's both. Okay, number 16 is also both. So that's a little more complicated sign, but it still has both characteristics. Both. Okay, 19, which is this one. So it's not closed because we have these two ends. And it's not simple because it crosses over. This is the example of a, this would be open but simple. This is open but not simple. This would be closed and simple, and this would be closed and not simple. So those are all the variations. So in this case, the answer to problem 19 is neither. Okay, decide whether each figure is convex or not convex. Okay, so we're doing 22, which is convex means it's kind of everything's pushing outward. So in this case, we have like a kidney bean shape. So this part's concave because it's bending in towards the center. This part's convex, but it's not all convex. So if we had something like this where it's always pushing outward. So anyway, this is not convex. And let's pick 24. So we'll change that to 24 because I didn't want to pick another one that's concave. So 24 is convex. It's like a kind of oval. Okay, so you can see that there's no indentations. If I did that to it, then it wouldn't be convex, because it's always kind of like if you blew up a balloon or something like that. Okay, so we'll go now to 28. Classify each triangle as acute, right, or obtuse, and also classify as equilateral, isosceles, and scalene. So 28, if you look at that figure, what do we see? Well, we see that all three sides are different lengths. So that means it's scalene. And we have one angle that is greater than 90. So that makes it obtuse. So it's obtuse and scalene. Okay, 31 has a 90-degree angle. So that means it's a right angle, a right triangle. And we see that the three sides are different. So there are no equal sides. So therefore it is a right triangle. And it is scalene because no two sides are equal to each other. Okay, 34 is another example of a right scalene triangle. So we'll actually change that to 35. Actually, let's do 33. So 33, you can see it has two sides that have the same length and a right a 90-degree angle. So because of the 90-degree angle, it's a right triangle. And because it has two sides that are the same, it's an isosceles. Isosceles. Yeah, I guess that's right. For some reason I was thinking I was pronouncing it incorrectly, but so it's an isosceles triangle. Okay, and then let's do 37. So 37 has two sides that have the same length. So hence they have two angles that are the same. So it's an isosceles triangle. And they give the two angles because if you take 50 and 50, that's 100. So the third angle as a consequence is 80 degrees. So we have 80 degrees, 50 degrees, 50 degrees. None of these are greater than 90. So when none of the angles are greater than 90, we call that an acute triangle. So it's an acute isosceles triangle. Okay, so I think we're going to stop there and come back once we get